we have studied about the preparation of alkanes from unsaturated hydrocarbons like alkenes and alkynes. Now, we will start with the second method, that is from alkyl halides. From alkyl halides. Okay. What are halides? Halides are fluoride, chloride, bromide, iodide. Okay. Generally, we don't consider fluoride because reactivity of fluoride is quite different from the other halides. So, we consider them. Chloride, bromide and iodide have similar reactivities, and fluoride has different reactivity. Okay. So, halides are collectively denoted by X. Okay. So, the first method is let us say Rx. R is for the alkyl group. Okay. Alkyl groups are generally denoted by capital R. So, let us say Rx. Okay. For example, this can be methyl chloride or ethyl chloride. Okay. So, there is one reducing agent, that is PH3SNH. There are other variations also like BU3SNH. These are reducing agents, and this is a strong reducing agent. It reduces alkyl halide to alkane, and it can reduce primary, secondary and tertiary alkyl halides, all of them. So, what are primary, secondary and tertiary alkyl halides? We had studied about primary, secondary, tertiary carbon atoms. So, it is similar. So, halide attached to the primary carbon is primary halide and so on. So, the second method is alkyl halide by sodium borohydride. This also converts alkyl halide to alkane, but since sodium borohydride is a mild reducing agent, it converts only primary and secondary alkyl halides, secondary and tertiary alkyl halides to alkanes. It is very important to note that NaBH4 cannot convert. This also converts alkyl halide to alkane, but since sodium borohydride is a mild reducing agent, it converts secondary and tertiary alkyl halides to alkanes. It is very important to note that NaBH4 cannot convert primary alkyl halide to alkanes, because according to the mechanism in which this reducing agent acts, the reactivity of the primary alkyl halide is much lower than secondary and tertiary, and since this is a mild reducing agent, it acts only on secondary and tertiary. Now, the third one is lithium aluminium hydride. Lithium aluminium hydride. It converts only primary and secondary alkyl halides to alkanes. Why? This is a strong reducing agent. This should have converted all types of alkyl halides. It does. But since tertiary alkyl halides have greater reactivity and this is also a very strong reducing agent, so it does something different. For tertiary alkyl halide, this converts tertiary alkyl halides to alkenes. Okay. Let's say this is a tertiary alkyl halide. Okay. So, if we put lithium aluminium hydride here, it will convert this to this. Okay, this is an exception case. So, let us say we have ethyl chloride and we give NaBH4 here. Since it is a primary alkyl halide, this will this be converted to ethane? It will not be converted to ethane because we had said that NaBH4 does not act on primary alkyl halides. Okay. So, these are some common reducing agents which converts alkyl halides to alkenes. Now, there is another method of converting alkyl halides to alkenes, that is by zinc and dilute HCl. This is an example. We have hydrogen and we have zinc and HCl. So, in presence of zinc and HCl, alkyl halides will be converted to alkane and HCl will be liberated. Okay. Similarly, if we take methyl chloride for example, then we get methane plus HCl. Now, there is a fifth method of converting alkyl halides to alkanes. It is a very important name reaction known as the Woods reaction. Okay. What is Woods reaction? Alkyl halides on treatment with sodium in dry ether gives higher alkanes. Okay. So, the starting alkyl halide will give a higher alkane, and it is very important to note this dry ether. This is a solvent, and what does dry ether means? Dry ether means solvent without moisture content or without water content. There should be no water in it. Okay. So, what is the reaction? Let us say we take Rx, this is one alkyl halide. We will take 2 moles of sodium or 2 equivalents of sodium, and we have another alkyl halide here. We could write 2 here also, but we are writing this to understand how the process works. So, it is like this. Now, these two sodium bonds with two halide ions and they get liberated as 2NaX. Let us say if this was chloride, okay, then we get 2NaCl. Now, when 2NaCl is liberated, then these two alkyl groups connect with each other and form an alkane. Okay. Let us see an example. Let us say CH3Br, 2 sodium and CH3Br. This will be in dry ether. Okay. This is very important. So, in presence of dry ether, we will get ethane and 2 sodium bromide. Okay. Now, from methyl bromide we are getting ethane, right? Methyl halide is giving ethane. So, we are getting an higher alkane. If we start with ethyl bromide, what will happen then? By this mechanism, two ethyl groups will join with each other. So, we will get CH3, CH2, CH2, CH3, that is butane, and as usual 2 sodium bromide. Okay. So, from ethyl bromide we get butane. Now, what will happen if we take two different alkyl halides? Let us say one is this and one is this. Okay. We have 2 sodium in dry ether. What will happen? Now, there we may expect that by joining two alkyl halides we will get something like this, but no, this will not be the only product. Let us see how many products are possible. Let us discuss with a easy example first. We have CH3Br and we have ethyl bromide. Okay. So, what will happen? So, first the easiest possible case that we can imagine, two NaBr will be liberated and we get propane, right. Now, whenever we conduct a reaction, we cannot take a single molecule of anything, right. We will take some amount, let us say 100 milligram or 200 milligram, but within that there are multiple number of molecules of a same compound, right. So, in the system only a single molecule of methyl bromide is not present, there are multiple molecules of methyl bromide. So, if multiple molecules of methyl bromide are present, then they can also form reaction like this and they will form ethane. Okay. Similarly, there are multiple molecules of ethyl bromide as well. So, when two ethyl groups join, it will give butane. Okay. So, from a single reaction we are getting propane, ethane, butane, 3 types of alkanes. So, by reacting different alkyl halides we cannot get any separate product. Okay. So, now if we consider this reaction, okay, let us number 1, 2, 3, 4, here also 1, 2, 3 and 1 methyl group here. Okay. So, the bond will be between the second carbon of 1 and the first carbon of 2. So, the second carbon of 1 and first carbon of 2. Okay. So, this is one molecule which is formed by 1 plus 2. Now, 1 can also form bond with another molecule of 1. So, it will be like this. Okay. So, this is the second possible case, 1 plus 1. We can also have this, right? Okay. This is the third possible case, 2 plus 2. Okay. So, this was the Wurtz reaction. Now, similar to Wurtz reaction, another reaction is there which is known as the Frankland reaction. Okay. It is totally similar to Wurtz reaction. The mechanism, reaction, products, everything are similar, just in place of sodium we use zinc here. Okay. Otherwise, it is all the same. So, the next process of preparing alkanes is from carboxylic acids. Okay. For the preparation of alkanes from carboxylic acid, there are two major reactions. One is known as the decarboxylation and another is the coal-base electrolytic method. Okay. So, in the next lecture, we will study about the preparation of alkanes from carboxylic acids by the methods of decarboxylation and coal-base electrolytic method. Thank you.